Yo, welcome back to the Nucleogenesis Project. My name is Dr. James Utley. I'm your resident codebreaker data scraper, and we are on part 6. So the Nucleogenesis Project, if you don't know, is found on the syndicate-labs.io website, and it is a temporal framework for eukaryotic nuclear blueprint archival and reconstruction. So what that means is developing a digital file, a nuclear blueprint manifest, so a digital file of a nucleus that can be used for synthetic biology in the future. And anyway, we are on part 6. If you want to check out the other episodes, go back and watch them. All right, and we're going to get down to it. We are on chain of custody cryptographic protocol. That's a section 2.4, and every interaction with the biological sample for nucleogenesis framework, whether it's physical handling, analytical processing, or data generation, it produces a cryptographically linked audit record. And the reason why is because this is temporally or over time, it needs to maintain a record, and these records are part of a log, right? So it's a ledger. It's a provenance log that captures not only what is done to the sample, but when, by whom, and what in what informational context. Because you don't know that in the future, like what is exactly needed. And as we're thinking about developing something from a blueprint, right? So I think the importance of time and space and the handling and all of that, it may be non-diagnostic, but it may be diagnostic. Who knows? So anyway, so this design provides a sample history, if you will. It's verifiable, it's tamper evident, and you can reconstruct it over a long horizon, long time horizon. And that's the idea of making sure that there is a standard that is met. Now, if you can see, we have an entry n variable here, and that is all of the string of everything that is needed for that one variable. So that denotes the operations performed, whether it's disposition, extraction, sequencing, or transfer. And you can see that represented in this audit trail down here, which is ideally suited or meant to be in a blockchain. So each block, and then you can maintain all of the blocks, in the essence of cryptographically keeping all the information that can be audited later. So an immutable ledger, which is blockchain technology for sure. All right, so the TN is the timestamp of the operation. The actor is who identifies the responsible individual system or instrument. So that's your actor N. Your data N captures the operation, specific metadata or derived outputs, right, which should to be later determined. And then the H entry n-1 is the cryptographic hash of the previous audit entry. So you see block before. So it's like basically keeping a cryptographic hash of all like the baseline anchor layer, the anchor data, right? Because remember, we have two fractions. We have a fresh fraction, and then we have a DBS fraction. And if you don't know what I'm talking about, go back, watch the prior videos. But by embedding the hash of the preceding entry, each record becomes cryptographically dependent on the entry history before it, right? Because you're looking to build it over long time horizons. And you're trying to compensate for the future technology that you don't realize exists. And this creates a hash chain. So the hash chain, which will log in the ledger any modification, deletion, or reordering of the historical records, and it will also invalidate things if it's not if the system is not adhered to in this in a blockchain format here or this audited format. It reduces the reliability, right? So this mechanism is put in place so it doesn't rely on the trust of the operators, but it relies on the integrity forced by the record itself, right? So in the future, by however things are segregated, meaning like humans operating testing, it doesn't matter because it cannot be immuted, and this information will exist in the futures. And that's why exist in an immutable audible form in the future. And that's the essence of having a cryptographically hashed information media that will then be able to build a nucleus. So you know that nothing can, so you as the individual that will hopefully be using this information to reconstruct a nucleus that will be able to print you new body parts or whatever you need, right? This is hypothetically, collect now, decrypt later, remember, but you have to be able to audit all the information to make sure that when you get to the downstream. So let's give an example. So if you're, well, we'll get into all of that later down in this paper here, but this is, remember that it's an immutable record, and that's what we're trying to do. Is we have been through two fractions, which is the biological fraction, which means the testing the information that will then be destroyed quickly because of the dehydration of the sample. And then you have the long-term, more biophysically stable stuff, which is embedded in the dried blood spot card, and that is kind of a reference for the future. And then you build this data layer, which is your anchor, which is a blockchain immutable record. All right, seems like a lot, I know. And as we go through this, it'll boil down better, right? But anyway, so now we're in algorithm 2. This is the second algorithm for the chain of custody identification verification. And basically it tells you that it's looking for what's expected, meaning the prior block and the information in the prior block to build on the next block. And if it doesn't, then it'll return the integrity has been violated, and then you can investigate that. But if not, it will return that it is verified, and then you're moving on that next block or that information block. So interpretation. The verification procedure confirms that the record sequence of operations is internally consistent and unaltered from point of origin. So when it started, or that T0 mark that we talked about in earlier videos, a successful verification implies that every operation applied to the sample occurred in a documented order and that no intermediate state has been silently modified. Conversely, detected violation localizes the precise point at which integrity was lost, enabling forensic investigation rather than the silent failure. And that's what it does. So it's just a ledger over time, because what we're doing is you want to maintain yourself, meaning the preservation of your own material. And how do you do that? You have to cryptographically hash it in blocks using a blockchain, verifiable technology, which is outlined here. And what that does is it tells you at what point was your block verified. And this is the trust list, because you don't want to trust any other human. You don't want to trust a government, an institution, or whatever. You just want to make sure that you can verify it yourself. And that's the empowerment mechanism, is that you can take your own biological material and you can verify it. And you can verify it at every step of the way. All right. Now, so with the nucleogenesis framework, the audit mechanism elevates the chain of custody from a procedural safeguard to a cryptographically enforced property. It ensures that biological material, derived data, and time-separated reconstruction workflows remain coherently linked, even in an adversarial, multi-institutional, or post-calamity context. So I'll read that again. Within the nucleogenesis framework, the audit mechanism elevates the chain of custody from a procedural safeguard to a cryptographically enforced property. It ensures that the biological material, derived data, and time-sensitive construct workflows remain coherently linked even in an adversarial, multi-institutional, or a post-calamity context. Keeps you in charge. And that is the essence of it. Okay, so now we'll stop here for the day, and we'll be on section 2.5 in part 7, which is next. With that, remember, my name is Dr. James Utley. I'm your resident codebreaker data scraper, and thank you for joining me. This is the Nucleogenesis Project. See you in the future. Peace.